Okay, so let's go ahead and get started, and then we'll see. If you guys have any questions, stop me along the way. I'm going to ask you guys a couple of questions. Hopefully, we can make it through with not too many bumps or bruises. Okay, so we're going to be talking about electromagnetic radiation. So, energy is going to be in the forms of electromagnetic and or electric and magnetic waves. Now, these are going to include all the things that you guys are kind of familiar with: your gamma rays, your X rays, your UV light, your visible light, which is white light, what we use to light up our house, our infrared light, um, microwaves, radio waves. So all of that's going to be included in this. And energy is going to be transmitted at the speed of light, which is 3.00 times 10 to the eighth uh, meters per second. Now, the thing is about light is that it's going to have wave-like properties. So it's going to be traveling in waves. And the other thing about light is that it also acts like a particle. So we have this dual wave particle dynamics that is going on. And since we're going to be talking about waves, we're going to be talking about there's a couple of things. We're going to be talking about things such as the velocity or the speed. Okay. We're going to be talking about the wavelength, and we're going to be talking about the frequency. Okay. So speed of light is going to be equal to lambda times nu. So this is this symbol here. I know it looks like a V. This symbol here, it really is nu. I'll spell that out for you. Nu, Nu. Okay. Now that's going to represent our frequency. And lambda is going to be the wavelength. So lambda is going to be a distance. Frequency, the units for frequency is going to be 1 over seconds. So that's going to be for frequency. We know that the wavelength is going to either be in picometers, nanometers, meters, and I guess occasionally micrometers. Okay, so those are the common units that we're going to be using for it. So we know that that's going to be distance. Frequency is going to be 1 over seconds. Okay, or you'll see it written as s to the minus 1, which is the same thing as 1 over seconds. Or you're going to see it written as hertz. So those are going to be the units. Now, 1 hertz is going to be equal to 1 over seconds. Okay, so they're equivalent to each other. Now, if we look at frequency, nu, and we look at the wavelength, this is called lambda. So lambda times nu, that's going to be lambda times, that's going to be wavelength times our frequency. Now, these guys are, since they're on the both sides and they're being multiplied by each other, they're going to be inversely proportional. So we know that speed of light is a constant. It's always going to be exactly the same thing. Okay, so it's always going to be 3.00 times 10 to the eighth. And so since we know that this is going to be constant, as lambda increases, what's going to happen to nu or the frequency?
It'll go down.
It's going to go down. That's right. Okay, so that's what inversely proportional means. As one of your variables goes up, the other one has to come down to balance itself out. Now, we're going to be talking about energy, and we're going to be associating a lot of things with energy. So, the way that we associate the speed of light or light with energy is we use an equation. It's, I guess I should probably write it. It's E for energy is going to be equal to H times nu. Okay, now again, nu is going to be our frequency. H is going to be Planck's constant. Okay, and so that's also going to be a constant. Now, in this case, energy is going to be directly proportional to the frequency. And so if energy is directly proportional to the frequency, if we substitute and solve for our frequency down here, nu is going to be equal to C over lambda. So we could say energy is also going to be equal to H. So in this case, the energy is going to, as the energy increases, the wavelength is going to decrease. And so they're going to be inversely proportional to each other. Okay? Okay. So let's take a look. So here we have the electromagnetic spectrum. And so this here represents wavelengths down here, and up here is the frequency. So the wavelength is going to be, take a look at these little waves here. We go from peak to peak. That's going to represent our wavelength. So that's going to be our lambda. Okay, so from peak to peak, that's going to let us know how far it is. Now, frequency is how many peaks that you have within a segment of time. Okay, so if we said that this is 2 peaks in a segment of time, so then our frequency would be 2 1 over seconds. So we have 2 cycles that would happen in 1 second. Okay, so if we take a look at this, our wavelength is down here. And so as our wavelength increases, we'll notice that our frequency decreases. Okay. Now, what's going to happen to the energy? Will we expect the energy to increase or to decrease?
Increase.
So as we move in this direction, we'd expect it to increase. Is that what you're saying? So as our frequency gets smaller, we expect our energy to increase or to decrease?
My bad, decrease.
We'd expect it to decrease because we know that energy is going to be directly proportional to our frequency. Okay, so E is going to be equal to H nu. So as energy decreases, our nu is going to decrease. So as our frequency decreases, our energy is going to decrease. Okay, so let's keep moving. So if you take a look at this, our lower frequency, meaning that they're going to be very small wavelength. Our higher frequencies is going to have very small wavelengths. So the wavelengths are going to be very, very small. So we have gamma rays here, we have X rays here, we have UV rays, we have IR. In between UV and IR, we have our visible light. Now, our gamma rays, the wavelength is going to be so small. And so they're actually so small that it would allow the particle to be able to penetrate our cells. And so this is leads to our gamma radiation. Have you guys heard of gamma radiation before?
Yes.
Yes. Where did you hear of gamma radiation from?
The Hulk.
The Hulk, exactly, the Hulk, right? So everybody knows the Incredible Hulk, and we often will associate it with the Incredible Hulk. So, but in the case of gamma radiation, it's so small, the frequency is so small that it's actually able to penetrate your cells and also the nucleus and shred it to bits and pieces. The gamma radiation does really bad harm to us. And so high levels of gamma radiation, even low levels of gamma radiation, causes us tremendous harm. Now, as we go with X-rays, right? How have you guys used X-rays before or been in a case where X-rays have been used on you?
Yes, X-ray's been used on me.
Yes.
Where does that happen at?
An X-ray center at the hospital.
At the hospital, okay?
Or the dentist.
Or the dentist, right? So we always associate it with the hospital or the dentist. And when they take those X-rays, what do they typically put on you?
A vest.
They put a vest on you.
Some sort of protection.
That's right. And so they put a vest on you because, again, if you take a look where X-rays at, the wavelength for X-rays, it falls in the range of an atom or a virus. And so, in other words, it's so small that it can actually do harm to us, again, harm to our cells. If you take a look at the human cell is about in the area of infrared, right? And so that's when our wavelength gets so big that it's not able to necessarily start penetrating our cells. So X-rays can cause damage to our DNA. And so that's why we use lead. Lead will actually block out the X-rays. And so you guys are familiar with UV light. So that's the light that we get from the sun. They tell you not to get too much of that because that actually starts to, again, could cause cancer in high levels. And then we talk about visible light. Visible light is that white light. Now, if you notice that visible light has all of these colors that are represented here. So that's called a full spectrum or a continuous spectrum. And so it's just like the rainbow. Okay. So we're going from a purple color or ultraviolet or violet to a red. And you notice that your ultraviolet, UV stands for ultraviolet, is going to be closer to your violet. And then your infrared is going to be closer to your red. Okay. And so this is the wavelength of that visible light. So our violet is going to be around 400, and then our red is going to be about 7. And then we have all the colors in between, right? And so they are all going to be representing a different wavelength, which also means that they're also going to represent a different frequency. So if we wanted to calculate, and let me write this on the board. Calculate the frequency, sorry. Okay, so calculate the frequency of orange light if it has a wavelength of 6.20 nanometers. Okay, and then I'm going to go ahead and give you the equation right now. So then you guys can start working out that problem. So we know that the equation that we just wrote on the board was C is going to be equal to lambda nu. Okay. And we know that C represents what again?
Speed of light.
That's meters per second. Okay. And NM stands for nanometers. 1 nanometer is going to be equal to 1 times 10 to the minus 9 meters.
Dr. Henry.
Yep.
It's C, so that's the speed of light, right?
Yep.
Equals, is that lambda? The lambda, that's the wavelength?
That's the wavelength. That's correct.
Okay, and then what's the other symbol right
It's
there?
it's nu,
Oh, new.
nu or frequency.
Oh, that's for the frequency. Okay, thank you.
From what I understand, to find the frequency, we have to derive the equation to nu equals lambda over wait no, nu equals C over lambda.
Okay. Okay. That's correct. And then what else do we need to do? There's another thing that we need to definitely make sure we take care of first.
Um, do we have to change from nanometers to meters?
That is correct.
And we do that by multiplying it by 1 to the 10, 1 times 10 to the ninth power.
That is correct. Okay. So we need to change our nanometers to meters. So, and you're right, we do that by multiplying. So we'll have 620 6.20 nanometers. Writing like a third grader here. So 1 nanometer on the bottom, and then we have 10 to the minus 9 on top. So then nanometers cancel out. And we're left with
Um,
There.
it says 620 and you put 6 were you taking?
Yeah, I'm fixing it right now.
Okay, I was like, wait, well, how did he get 6.20? Okay.
Yeah, but I'm struggling right now, so let me see if I can get that.
Okay.
I'm gonna rewrite it because it'll take me all day to sit there and write that down. So it's 620.0. That's a 6 here. Okay. Okay, so
Well, would we change it to 6.2? Because it's gonna be like, is it gonna be like in scientific notation
yep,
or?
that's right. We are gonna change the scientific notation.
Okay.
See if I can- okay. Okay, so we're gonna end up with times 10 to the, oops. Sorry, I'm trying to use I'm struggling today. Into this -7 meters. Okay. So then, as you said, we're going to use our new. Going to be equal to speed of light times 10 to the 8. That's meters over seconds divided by 6.200 times 10 to the -7 meters. So then meters are going to cancel out. And then we're just going to be left with 1 over seconds. So then our velocity is going to be, math real quick. How many sig figs should we have?
Two.
3?
If we look at our number here, Yeah, so if we have look at our numbers here, and then our constant. It's going to be 3, right? Because this one, it would be 4 sig figs here, and then that one would be 3 sig figs. Okay, questions?
I have a question about the -7.
Okay,
Because I see it's 620.0 and then it's times 10 to the -9 and then it went to -7. And I
That's
know
right.
that has to do with, is that because we're multiplying?
Yep, that's because we're multiplying, because this is 620. So then
Right.
to put in scientific notation, it would be 6.2. So, I mean, 6.2.
Oh, the places that we move. Okay, I got it. I got it. All right, thank you.
No problem. Okay, so let's do another one. Let's say,
We don't have to, what do you call it? Convert our answer to hertz?
hertz would be the same as 1/seconds. So you could just put HZ and something.
HZ? Oh, okay.
Yep. Yeah, so 1/seconds is the same thing as hertz. Okay, so, and then let's do this. Okay. And that's 1.5 times 10 to the 14.
For Planck's constant, is that negative 34?
Yes, it's negative 34. Okay, so what are we going to do?
We're gonna multiply Planck's constant by our frequency.
Okay. Six point 626 times 10 to the minus 34. And that's joules hertz. And you're going to multiply by the frequency, which is 1 point. Oops. Sorry, that should be joules hertz, joules over hertz. Okay, so then we end up with, I'm going to continue down here since
I got 9.39 times 10 to the negative 20th joules.
So
then how many-
energy is in joules, sorry.
that's right, it should be in joules. That's right.
Okay,
He said 9 times
39, sorry.
10 to the negative 20 joules. Okay. Question? Okay, good. That's it. Okay, so we talked about visible light being a continuous spectrum. What we mean by that is that the colors kind of bleed into each other, and so it's continuous. So there's, at every frequency, there's a wavelength that is going to be associated in that range. If we're talking about a line spectrum, we're going to have discrete lines that are going to show up. So, like for instance, if we take a atom and we excite it with electricity in a bulb or excite it with some energy, what's going to happen is it's going to provide a line spectrum. and not every element has a very distinct line spectrum. They don't look exactly the same. And so we call that a discrete line spectrum, or we'll call it a line spectrum. And so what's happening in that case is that we're putting energy, exciting the electrons. And then those electrons, when they drop down in energy, they release that light. And so we'll see that particular line. And so how many of you guys have kids or brothers and sisters that are really young, or nieces and nephews that are really young?
I do.
You do? So what happens when you feed them a whole bunch?
When you feed them what?
A whole bunch of candy?
Oh, they go crazy.
They
She
go
goes
crazy,
crazy.
right? They go, ah, and they're running around the room and screaming and hollering and jumping all over you, right? And then at the end of the night, what happens to them?
They crash out.
They crash, right? And so that's exactly what happens with the electron. So the electron is going to get excited, and then it's going to crash. And when it crashes, it emits light. And so that's what we see in our spectrum. So let me show you what that's going to look like. So I guess I have to talk to you about a wave. So we've already talked about the wavelength, and we've talked about the frequency. So this is the wavelength, two different wavelengths, and these are the frequency. This guy would have 2. This guy would have 1, 2, 3, 4. 4 within the same amount of time, right? So the wavelength is from peak to peak, or trough to trough, and then that gives us that distance. And then the frequency is how frequent those waves are occurring within a time interval. This here is an example of white light being separated by a prism into a continuous spectrum. This here is the gas hydrogen being excited, and then it forms discrete line spectrum, right? Or a line spectrum. And so because it's hydrogen, there's only so many electrons, and they're going to get excited, and then they're going to drop back down in energy. And then they're going to show the different lights from the energy that's being projected. So this is an example of the hydrogen. This is mercury, and then this is neon. And you can see that they have very distinct line spectrums. And that's going to be with all atoms. They're going to have very distinct line spectrums. Okay, so this brings us to Bohr's model of quantization. Then again, I'll show you the whole concept of the electron later. So, or Bohr's model of the hydrogen atom. And so in the case of Bohr's atom, so we know that in the middle of the atom is the nucleus. And we have the electrons that are going to be orbiting around the nucleus. And so, but if we look at that atom, the most of the space is going to be empty space of the atom. So we're going to have that electron density cloud on the outside where the electrons are orbiting, but we're going to have a lot of empty space. Now, the way it works out is that the orbiting pattern of the electron is going to be based upon energy, right? And so we have what we call a ground energy state, or a ground state, where the electron is at when it's low energy. When we excite it, it gets put up into another orbital or another spot that it's higher energy, okay? Or we'll say another period of energy, okay? So we're going to be talking about how that's going to be happening. Now, the thing is that when we think about energy, we're going to have it quantized, meaning that it's going to be in discrete sets of values, okay? So we're going to be exciting electrons to discrete energy levels. And then when we talk continuous, that means that they're all going to kind of run. We're going to have every value known until infinity. Okay. So what we're talking about is kind of like this individual walking on the stairs. So this here would represent the continuous, right? So there's no stairs. So she's just walking up that gradient. But in the case of quantizing, it's like steps. So each one represents a different step of energy. So if we look at our model, the Bohr model of the hydrogen atom, so here, this is the nucleus. So this would be our ground state, our ground energy state. N2 would be our second period, or the next energy state. N3 would represent our third period, or the next energy state. N4 would represent the fourth period and the next energy state. Now, the way it's set up is at its ground state, that's going to be the lowest energy level possible. Atoms, are going to try to keep a low energy profile. So they like to be in that low energy state. As soon as we excite them, we put them into their excited state. So the concept of jumping from one energy level to another energy level without passing through each of the energy levels through that process is called a quantum jump or a quantum leap. I don't know if you watched, there's a show called Quantum Leap, where this guy is jumping throughout time, different time periods, being different people. So it's the same concept, but on an individual person rather than on the electrons. So the electron is just, it gets enough energy and it's able to appear in that next state. Okay. So in theory, what we're saying is that if we excite, let's say you guys have a turkey. Do you guys cook turkey for Thanksgiving? Or for Easter or?
Yes.
Yeah.
Okay. So if we excite all the electrons in your turkey that's in your oven right now, if we excite it all the right way, we can actually have your turkey end up in my stomach, without me coming over and eating it all. Okay. And that would be finding the right energy frequency for every electron in that turkey for that to happen. So that process is called, I guess it's teleportation, right? So we're teleporting, or we're what is it? Yeah, it's teleporting from one point to the other point. But it's the concept of using the right energy signature to get there. We're not there yet, right? Hopefully someday we will be there, because man, I hate commuting, it's take its toll on me. So as soon as we get there, the better off we'll be, or at least I will be. Okay. So we've talked about ground state. Ground state is the lowest possible energy level of the electrons for all electrons, and that's going to be their ground state. The excited state is when those electrons absorb enough energy to push them up to another state. And because the excited state can't be stabilized, they're going to drop back down to that ground state. So in that case, we're talking about your turkey. It'll end up in my stomach, and then it'll end up going back to your oven. So this is a illustration of that. The electron, this here represents the electron. It's going to absorb energy, and that's going to cause it to go to the excited state. Soon as it crashes back down, it's going to emit that energy, and it's going to give us a photon of light. And then that photon of light is what we're going to visualize, what we're going to see. And that's what we see with that line spectrum. Any questions so far? Okay. So Bohr, basically, he's considered the father of quantum mechanics. And that's mainly because he came up with this concept of the different energy levels, and that it represents energy levels that the electrons are going to be moving in. Now, that energy level, or those levels of energy, we call them periods on the periodic table, but they're going to represent the principal energy. We also will call them the principal quantum number, and that's going to be represented by the letter N for right now. So when we talk about quantum mechanics, so we're going to be talking about that principal energy level. We're going to be talking about the sub level. We're going to be talking about the orbital, and then we're going to be talking about the what we call the spin in the orbital. So those are going to be your four principal quantum numbers. And we're going to talk a little bit more about that. Here we say the number of electrons in the orbitals. So that represents the spin, sort of. So we'll talk more about this. Now, the principal energy level, that's going to be N. That's going to be our period. That's going to represent the period that we're talking about for that particular electron. So mathematically, there is no end to a principal energy level. But as of right now, we only go up to 7. In the future, we don't know. We may be able to find or create more atoms that we may be able to go beyond 7. And I'll show you that here in 1 second. But when we talk about that principal energy level, it's going to be starting at 1, and it's going to increase to 2, then 3, then 4, then 5, then 6. So that's going to represent the different energy levels that we can get. So if we go to our periodic table, maybe if we go to our periodic table, okay, do you guys have your periodic table available? Okay, so if you look on the side, these are periods. At the top, these are groups. And so our periods, those are going to represent our principal energy level. So if we have an electron in period 1, so then that would be our first quantum number, 1. Okay? So next we have these sublevels, or we would call them subshells. So we have the S, the P, the D, and the F. If we go beyond that, the S, the P, the D, and the F, then we go to G, H, I. It would follow that. But right now, we only go to the S, the P, the D, and the F subshell, or sublevel. And let me show you whether that's at on the periodic table. Okay, so this here, so that's going to be our S. This here, that's going to be our P. And so this helium is really going to be over here next to the hydrogen for this purposes. Okay. So in that S, this is going to represent the D. And these down here, that's going to represent the F. Let me fix that. So these 71 and 103, these are really in the D. So these guys are really over here in this spot right here in the D. Okay, now this is what the periodic table really looks like. Let me show you. Okay, I'm going to clear it again. Then I'll try it again. Okay, so now here you see the S. Here you see the S. That's the S. This here is the F. This here is our D. This here is our P. Okay. Now, I'm going to write this up here. So the S, how many columns are in the S part?
2.
2. So the S can hold 2 electrons. The P, it can hold how many electrons? How many columns are there?
Is it 5? I can't tell because I can't see the.
The last one?
Yeah.
Yeah. See if I can make it a little bit smaller so your screen can see it. Hold on. Because of our faces are in the way, right?
Yes.
Yeah. Okay, here. So here's the P right here. Can you see it?
Yeah, you're asking for D. I thought you said P.
P, yeah. No,
Oh.
I said P. I said P.
You
Right
did.
now it's showing you where the D is at. Let me slide that over so it doesn't. Everything has been shrunk a little bit. Sorry. So that's our D over here. And then this is our P. Okay. So that's total of 6 electrons. Our D, how many is in our D? How many columns?
I think I counted 10.
That's right, 10. And how many Fs? Let me go back so you can see the F now. That represents the F.
Is it 14?
That's right. Oops, I don't know what it's doing there. Hold on. Okay. So we have 14. Okay. So that's how many electrons can be held in each of those subshells. So the S can only hold 2. The P can only hold 6. The D can hold 10, and the F can hold 14. Okay. So when we talk about those subshells, this. So when we talk about our subshells, so we have the S, the P, the D, and the F. So as we said, the S holds how many?
2.
Let me use this. I'm using 2. And then the P,
6,
the D,
10,
and the F.
14.
Okay. So that's how many electrons can be held there. Okay, so when we talk about our subshell, we also need to talk about the principal quantum number. So the subshell represents our second quantum number. We'll have a number that's associated with it, but for our purposes, we're not going to worry about that quantum, the number, but we're going to recognize it as the S, the P, the D, and the F. Okay. So the principal quantum number has to go with it to let us know where the electron is at. So if we're talking about, let's say we're talking about magnesium, right? So then we're talking about this electron in magnesium. So we would say that that would be in our 3s subshell or sub level, okay? So we'd write it as 3s, okay? Because that electron for that last one is going to be in the 3, the period, third period, and it's going to fall under the S subshell. Okay. So when we look at these subshells, so we only have for the very first one, for hydrogen, there's only one level or one subshell. So you have the 1s. When you get beyond hydrogen, it gets bigger. So then we have 2 at the 2, principal level 2, second level. So then we could have the 2s, which is going to be less in energy than the 2p. So the 1s is lower in energy than the 2s or the 2p. Okay. Then we go at the third energy level, we're going to have the 3s, the 3p, and then the 3d. Then at the fourth energy level, we're going to have the 4s, the 4p, the 4d, and the 4f. Okay. So let's try to put that in perspective with our periodic table.
So moving from left to right, the energy increases. Or not the energy, the electron. Is it the electron?
It's the energy. It is
The energy, right? Okay.
yes. So it'll be the energy will be increasing. And so you want to think about it. If you're an electron, you always want to try to keep a low energy profile. So if we keep a low energy profile, that means we want the lowest possible energy, right? And so you always want to fill up your lower subshells first. And then if you need to fill up your bigger ones, you will later on. Okay, let's see if I can get everything in here. So I'm going to put it the way it normally is on a regular piece of paper. Okay, so this is the periodic table. Sorry. And so what we're saying is that on that very first period, we have only one S. So that would be the 1s energy level. This here would be the 2s, then this would be the 2p over here. So then we have the 3s. This here is the 3p. The 3d starts here. Even though it's on the fourth energy level, it starts 3d. And then this here is going to be our 4s. This here is going to be our 4p. So if we're putting electrons in, we're going to be going in, we're going to go in order. We're going to start off with the 1s. Then we're going to go to the 2s, then the 2p. Then we're going to go to the 3s, 3p. Then we're going to fill up the 4s first, and then the 3d. Okay. Then the 4p. Okay. And so if you take a look, that's what it's showing us here. So this is our 3s, this is our 3p, this is the 4s, then you fill up the 4d, then you go to 4p, then you go to, well, there'll be others in between here before we get to that 3d, there'll be another, sorry, there's a 4d, 4s, 4p, and then we'll have 5s, and then we have 4d, and then we'll have 4p. I mean, yeah. Right, 5s, 4d, and then 5p. Okay. So if we take a look, that's going to be the case until we get to like our 6th row. Okay, so down here, we'll continue with the okay. So as I said, 5s. This would be the 4d. This would be the 5p. This here is going to be our 6s. And then when we get to our 6s, we're going to come down here to our f's. Then this is the 4f. So it's going to be like 2 off from our period. Okay. And then we have this here would be the 5d. And of course, this would be the 6p. Okay. And this is going to be important when we start writing our electron configuration, which I'll show you here in a second. In a few. So let me go through 2 more slides and then we'll take a break to let our minds relax a little bit. And I need to get a little more caffeine in my body. So okay, let's do this. Okay, so we talked about those energy levels. So we're going to be increasing in terms of energy levels. So we've talked about how many electrons each can hold. Now we have what we call orbitals, right? And the orbitals would be the next part of our quantum numbers. So each orbital can hold 2 electrons. So we know that the s subshell has how many electrons, or can have how many electrons?
2.
2. So it only has 1 orbital. The p can hold 6, so it only has 3 orbitals. The d has 10 electrons. It has 5 orbitals. So if you look at an orbital, if you kind of think of an orbital of like a love seat can only sit 2 people, right? And so the s sub level has 1 love seat. And so what's happening is that those electrons, you have 2 electrons that are in there, and they're basically rotating in that 1 orbital. They're going to have to be opposite spins of each other so that they don't collide. So they're going to constantly be opposites of each other. And then that's the same thing with the p. It has 3 orbitals. You could have 2 electrons in each orbitals. Each one has to have an opposite spin. D, the same way. Okay? Are there any questions so far?
So it's 2 electrons per orbital.
2 electrons per orbital. And since S can only hold 2 electrons, it only has 1 orbital. P, it can hold 6 electrons. It has 3 orbitals. D can hold 10 electrons, so it has 5 orbitals. And F has 14 electrons, so it has 7 orbitals. Okay. So you'll notice that they're increasing by multiples, like by 2. So, you have 1, then you have 3, then you have 5, then you have 7. If there was a G, that would be what number?
9.
Okay. Okay, so this here represents how the orbital is going to be rotating around the nucleus. At least this is how Bohr perceived it. So you can see here there's the nucleus, there's an electron rotating around it, there's another rotating around it, and so forth, so on and so forth. So these represent the different orbitals. Now, this is what the quantum model actually represents. And so you see a cloud density, right, of electrons going all over the place and things to that extent. After they basically start fine-tuning that cloud, what it looked like is this is what the S orbital looks like. So it looks like a sphere. The P orbitals, they look like dumbbells. You have 1 in each of the different ones. So these orbitals can hold 2 electrons. Each orbital can hold 2 electrons. So this is what the D subshell orbitals look like. So the 5 orbitals, this is what they look like. Now, the way it works is that, how we have the 1s and then we have the 2s and, it gets bigger, right? So the S subshells are going to fit within each other. So have you guys seen like the Russian dolls, like the little dolls that have a doll inside of a doll inside of a doll?
Yes.
Yeah. Okay, so that's kind of like what happens with the orbitals. So the 1s is going to fit inside the 2s, which is going to fit inside the 3s. Now these are getting bigger, but they're also going to be higher in energy. So the electron in the 3s is going to be higher in energy than the one that's the 1s. Okay. So the Pauli exclusion principle says that you can only have 2 electrons occupying an orbital at most. You can have none, or you can have 1, or you can have 2, but that's it. That's all you can have. So that's what the Pauli exclusion principle basically says. You can only have the maximum of 2 electrons in an orbit. Now we're going to be talking about electron configuration. And so since we know our periods, and so those are the numbers on the side, which represent different energy levels, which represent the different energy level. Now I'm gonna show you how to go through the process of doing electron configuration for an atom. Okay. Now the rules are you always want to start filling the lowest energy level first. So that's at ground state. Fill that one first. Then you go to the next highest energy level, to the next highest energy level, and to the next higher energy level. Okay. We also know that you can't have more than 2 electrons in an orbital. So the maximum amount of electrons that you could have in the S subshell would be how many?
2.
2. That's right. It'll be 2. And so when we're going to arrange it, we're going to arrange them in the order that they're going. So we're always going to build them up. Okay. So let's go ahead and try to do one. And I'll do one, and then I'll have you guys do one. How about that? Then we'll take a short break. Come back and see if we remember anything that we just did. Okay. So let's say we're looking at sulfur. Sulfur is the one that we're looking at. So I'm going to go ahead and circle sulfur on our periodic table here. Okay, so the way that we go about it is we write the element that we have first. So we know that we have sulfur, so it's S. Can you guys see that? Up top, the S. Okay, then we'll put our brackets. So we'll start off at ground state, which is 1. So we have 1 S 2 because we have 2 electrons. We have a total of 6 electrons that we're working with. 2 of them are going to be in the 1s, and then we're going to go to the next row. So that represents this electron and that electron. Then we have the the second period, and then we have the 2s. This here is going to represent our S. E. Here is going to be D. That's what we're going to worry about right now. So we have 1s, 2, 2s, 2. So that gets rid of these guys. And then we have 2p, 6. So then that represents here, all those. And then we have 3s, 2. And then 1, 2, 3, 4. So then 3p4. And so that's how we'd write the electron configuration. Okay, that would be the electron configuration for this atom for sulfur. Okay, so what I want you guys to do is let's have you guys do aluminum, Al. Okay. Okay, so what are we going to do? What is the first one? So we're going to start at ground state. So then it should be start off at what?
1s2.
1s2. Okay. And then
Then is it 2s2?
that's right, 2s2. Let me erase these down here so that we can work our way through. Okay, so we're at 2s2, and we're trying to get to aluminum. This is our goal.
So then 2p6.
Okay, so that's getting rid of those electrons. Okay.
It'll be 3s2.
That's right. And then this last one for aluminum.
And then is it 3p1?
That's correct. Okay. And that's how you do it. Okay, questions? Okay, perfect.
Oh wait, I
So,
have a question, sorry. So
okay,
we always start at the ground, the 1s2
that's,
for all of the electrons, I mean for all of the elements.
yep.
Okay.
Okay. And then, but I'll show you a shortcut, a shorter way of writing it. So you don't have to write all of them. We can get it right, make it a little bit shorter. So, but
Oh,
I'll show you that when we get back. Okay, you guys ready? Let's see. So we're gonna do, let's do zirconium. Okay. So let's do it the long way first, and then I'll show you the shortcut. Okay, so we start at I'm gonna go ahead and put the element down. Okay, where are we gonna start at?
1s2.
2. Okay. And then, so that takes care of this. That
Then
first
it'll be 2s2.
2 S 2. Okay.
And then would it be 2p6?
Yep.
Would it be
2B6.
right? And then next would be 3s2.
3S2.
And then be 3, would it be 3p1?
Now we're going to zirconium, so not 3P1.
Wait, where's zirconium? Oh,
Yeah, we got a ways to go. So
oh,
3P,
wait, 3.
3P what? If it's full, how many can the P orbital hold?
2.
P, not the S.
Oh, wait, 6.
6, that's right. So 6, since it's full.
Oh, yeah. I don't know why I was thinking 1 for some reason. Okay, so
Yeah.
3p6. And then after that, would it be 4s2?
That's right. Okay, so then that takes care of here. And then this one down here would be,
3, is it 3d10?
that's right, 3D10. Okay.
And then do we go to 4s1? I mean,
Not 4,
4s2? No?
4P.
Is it
Over
4?
here. It's 4P. Yep.
Oh, okay, 4p.
Yep. 4P. And what's the most that that can hold?
6.
Okay, so then that covers here. Okay,
Is the next one 5s2?
that's right.
And then is it 4d10?
Not 4D10, but 4D. We're just going over to zirconium. How many is over there? To the one I have circled.
Uh-huh. How many what?
How many electrons are to there? So if we did the S, right? So 5S2, and then
Uh-huh.
we have 1, 2 left over for the 4P. I mean 4D. 4D2.
42? Oh, okay.
Yeah,
Okay.
because we're only going to zirconium.
Okay.
Okay.
40. Okay.
Okay. So does that make sense? Do you guys see it?
It's still a little confusing, but I kind of get it.
Okay. What about you, Noah and Magdalena?
It's a little tedious.
That's a little tedious. Okay. Okay. So let me show you the less tedious way. So you put the element like we did in the past. We're going to go to that element on our periodic table. So here's our zirconium. Then what we're going to do is we're going to go to the nearest noble gas that we passed. So these are the noble gases here. Okay, so these are all the noble gases. So here's zirconium. So we're going to go back until we get to our nearest noble gas that we've already passed. So then that would be krypton. So then what we're going to do is we're going to put krypton in brackets. And so we're going to say like krypton contains all the electrons that are all the way up to itself, to krypton. So they're going to represent, that bracket is going to represent all of these electrons, except for that 5s and that 4d. So then here, after we get to that krypton, Kr, then we start going. We start at that point. So we'd have 5s2 and 4d2. Okay, and that's how we'd write it. So zirconium. So this is going to represent all of these electrons up here. So that's what that represents. So quick way of writing it just like that. Okay, questions?
Okay, so you said we have to go to the nearest noble gas?
That we've passed. Yep.
Okay.
That we just passed. Yep. And then you write that down and then you act as if you're going to the next step. Then it's the 5s2 and then the 4d2. Okay. Okay, so let's see if you guys got the hang of it. So let's do we'll do 10. Let me erase everything else. 10. Okay, so now we know where 10 is at. Okay, so rather than doing it the long way, we're going to go back to our nearest noble gas. So that would be krypton. Okay, so then what would be after krypton? We're starting at this point. We're going to go back here to the 5. Okay, so what would be next?
So is that one 5s2?
5s2. Okay,
Then would it be 4p6? Or
4p or 4d? That's 5s2, that will take care of this guy right here. And then what about this area right here? What is that area?
oh yeah, that's the 4010.
4d10. Okay. Okay. And then after the 4d10, so that's taking care of this here.
And then would it be the 5p6? 5P, would it be 5P2? Or
Yeah.
do you have to go to the 4P?
Nope, 5P2, that's right.
Okay.
Okay. There we go. That's how it works. Okay, so we're going to do one down here. So we're going to do selenium. And so I'll show you how to do that. And then I'm going to have you guys do uranium. Okay. Okay, so we're going to do this the short way, or we call it the noble gas core method. So, trying to get my pen already. Okay, so we're doing CE. So what would be its noble gas core?
Radon.
Radon? Yeah.
Okay. Okay. Okay, so then that, oops, not radon, that's radium. Hold on. RN. Fix that. Okay, so we have RN, and then, so are you guys sure it's radon? Because remember, this guy is technically, it's technically in the third, I mean in the sixth period, technically. Then this guy comes back up,
So would it be, I don't know how to pronounce it, xenon?
xenon. That's right. Sorry about that. Struggling with my pen here. Okay, so we want it to be Xn. Then you need to get to the periodic table again. You know, it's so funny. I love technology, but I hate technology.
I feel you.
Okay. We have Xe. And
What does
then
it start with 5S2?
now remember, it's down here, right?
Oh, so 4S2?
Nope.
Wait.
So it's down here, but it's part of this row, right? So you see where it says 6, and then
Yeah.
it comes back up here 6, right? So we're following this path right here, going here. This is where we're going. What is that period there? After
That's
xenon? 6. I know it's hard to see because I've written all over it. Let's see. So 6s2, and then we go down here. What is this period? I mean, what is this subshell called down here? Right here.
That one is 6D? Wait.
Nope.
No, wait.
The D is up here. So what is this called down here? These, how many are there? Not in don't count this last two.
There are 14.
14. So who has 14 electrons?
The F. Oh, is it, what is it, 6F? 14?
So no, it would be 4F,
Oh, 4F.
4F, 14. Not 14, because we're not going all the way to the end. We're going just to the CE. That's where our target is. So then that'll be 1. That'll
2.
be, okay. Okay.
So with this method, like the noble gas core method, there's
Yep.
only gonna be like two, how do you say it? Like two subshells?
Two sections. No, it just depends. It just happened because this one is, we stop at CE. If we
Okay.
stop over here, like at lead, then there would be more than that.
Okay.
Yep. Here, let's do that one instead of doing the uranium. Okay. So I'm gonna erase it. Then we'll see what we can do here. Okay, so we're gonna do lead instead of uranium. Okay, so then I'm gonna go up here and write our okay, and then we put our bracket. I mean our decimal, our colon, and then our bracket. So what's going to go in our bracket? Here's lead. What noble gas is before lead?
Would it be the xenon?
It would be the xenon again. That's right. Okay. So we're going to start at our xenon. So then what comes after xenon? It goes here to 6. So then what is it next?
6s2.
Okay. So then we're going to follow our atomic numbers, increasing order. So then we come down here. So what is this?
Is that the 6F14?
Not 6. It's always 2 less. That's the one that you're
4?
starting on. 4. 4F14. I try to write on everything. Okay. Now I screwed up everything. Struggling with this pen. We're going lead, PB, bracket, and then we had xenon. Then we had 6. Okay, try this again here. I get trigger happy with my little tablet that is connected. I haven't learned how to control my pen. I feel like a third grader here. Love technology, but hate technology. So we had, as I said, PB. Then it's XC, xenon. Then we had 6s2, and we decided it was 4F. What is the maximum that we can hold in our F?
14.
14. And then, so that takes care of all of this guys down here. And then we come up here. So this is what would this place be here? And remember, we're going to lead. So what is this area right here that I just,
That's,
you know,
is it 60?
it is not 6, but it's 1 less,
Oh, 5D?
5D. 5D, how many can the D hold?
10.
Okay. And then, so that takes care of all of those at 5D. Okay. And then
Is it 6P2?
6P2. That's right. Okay. That's it. Let me move that 2 over so it doesn't look it's so randomly placed. Okay. Okay, that's basically how you do it. Right? Any questions? Okay. I will keep moving then. Okay. Oh, sorry. Sorry for yawning so much. For some reason, I am feeling exhausted, extremely exhausted. So this is just showing you the order that you would do it in. So we'd have our 1S, then our 2S, 2P, then our 3S, 3P, our 4S, 3D, 4P. And so you guys can see the how it's occupied, what level it's occupied at. So, so this here is an image of the electron surfacing circling the nucleus. And so just based upon this, I probably assume that we're probably in the d orbital. And then the part that we've seen is just that donut around in one of the d orbitals. Okay. So at this point, you should kind of already figure this out. So like if we were doing hydrogen, so this here represents that principal quantum number. Then this represents the sub-level or subshell. And then that's how many electrons that we have in that or sub-level. Okay. So these are some of the ground state electron configurations for these elements. And so test yourself out, make sure you got a good grasp on it. We've already talked about how to use the core electrons. And so going to the nearest noble gas, and then after that, that's before the element that we're talking about. And then we write the electrons that would be following. Like what we're doing here with neon. Okay, so this is neon's core configuration is this. We did aluminum, which we did earlier. It has this first part, and then the S2, and then the 3P1. So all of that together would have made aluminum, but we can write it in a smaller or a shorter context by using the noble gas and then the electrons that will be followed. And so here's an example where argon is being used. So here's for zinc. So then we have argon, and then we have 4s2, 3d10. Okay. So this here is just an algorithm of how to write electron configuration. So always first identify the element that you're talking about on the periodic table. And then you're just going to work your way through, starting with the ground state to the state that it's on. And always remember your d orbital. Your d orbitals are going to be 1 behind the principal quantum number. The f orbital is going to be 2 behind the principal quantum number. So then as you go through, you're going to write it from from left to right, and then filling up the lower energy levels first and building up to higher energy levels. And then you want to write your subscript that you're going to have in each of your energy levels. And then you want to count your total electrons. Okay. Now, with electron configuration, also with everything else in chemistry, there are always going to be some exceptions. Let me show you the exceptions. Two of them are right here, chromium and copper. Oops. Okay, so let me show you how they're exceptions. Let's go to the periodic table. Okay. So here on the periodic table, we're going to be looking at chromium, and then we're going to look at copper. So if you take a look at chromium, chromium has 5 electrons that are in a d orbital. I mean, sorry, 4 electrons that are in a d orbital in the 3d orbital. Circle them. Okay, so for it to be more stable, it would prefer having 5. So that basically means that every orbital can be filled if we do it that way. Not filled, but have an electron in it. So it'll make the atom more stable. So what it does, it borrows an electron from the 4s and it moves it up to the 3D. So then when you're writing the electron configuration, for chromium, Cr, so what we're going to do is put Ar, because that would be our nearest noble gas. So, and then we'll work our way through. So then normally we would have 4s2. So for right now, I'm going to write it down. And then that's going to be 3D. And that's 1, 2, 3, 4 normally, or what we would think would happen. But what really happens is, since it likes to only have 1, it's okay with only having 1 electron in the D, because it brings up the energy so that they're about the same as the 4s and the 3D, just in this case. So then it'll put 1 electron in the 4s. And then it'll lend the other electron to the 3D. So then we'll have a total of 3D5. Okay, so that's what chromium does. Cr. So copper, which is Cu, so it's going to have the same core, argon. Let me fix that. Cu looks horrible. I am really struggling today. I think I'm getting a little sick. My brain isn't working right. So we're going to have, as I said, argon. And then what's going to be next after argon?
It'll be 3D. 1.
Okay. I heard 4 What was that?
Oh, I thought it would be 3D9.
No. So first we got to do the 4 first, right?
Oh, uh-huh.
So it's 4s. So after we go to Argon, we want to come down here. So it'll be 4s. And you're right, it's going to borrow 1 from the 4. And then it's going to be 3D instead of 3D9. It's going to be 3D10.
10. Yeah.
So it's going to actually take that 1 electron because it prefers to have it in that D, keeping it completely full. So it makes it lower in energy.
Okay.
So those are your 2 exceptions. So if you look at it, anything that's going to be in this row is going to be an exception. And anything that's going to be in this row is going to be an exception. Okay? I mean, that row, column. Like I said, struggling a little bit today. So anything in this column and anything in this column. Okay? Okay, good. So we'll keep moving forward. Okay, so write the electron configuration for chlorine. Okay. Okay, where are we starting?
Are we doing the noble gas?
Yep, let's do our noble gas first.
So would it be neon?
Okay. And then,
Would it be 3s2?
okay,
And then would it be 3p5?
VP5. Okay. Okay, that's it.
Okay.
Okay. Good job.
You know what? On the on where it says writing electron configuration on the step 2, it says neon 3s, but it doesn't have the 2 superscript. Is that
Yeah.
like the same or no?
Glad you caught that. Okay. Good job. Oh, I guess we weren't finished with the steps. That's why I did show it. So, okay. So, develop the electron configuration for cobalt. I keep eating. I didn't get a chance to have lunch today, so I went from a meeting to class. Okay, so what is our core?
The argon.
And then
It'd be 2s2.
are you sure?
Wait,
2s.
argon.
So remember, you're going to start out in the next row after argon.
Oh, so then is it 4s2?
That's right.
I don't know. My brain is starting to not work either.
Yeah. For S2.
And then would it be 3D7?
Okay. That's right. Okay, so there's our 4s2 here. Then it's our 3d7. 1, 2, 3, 4, 5, 6, 7. There we go. Good job. Okay, so then now we're going to be talking about valence electrons. So when we talk about valence electrons, excuse me, we're going to be talking about the ones that are in the highest s and p orbitals. So in the case of phosphorus, it's going to be these last 5, right? So this here is going to represent the number of valence electrons. So we have 2 and 3 here. So we have a total of 5 valence electrons. Now, valence electrons are going to be the electrons that can do the bonding. So they're going to be able to bond. So what you're going to be using are the electrons that are free to bond. If you're using the core, let's say we're using a noble gas core. So in this case, that's would be argon. And then 3s2, 3p3. Okay, so, and that'll be in brackets. Okay, so these electrons that are not in that core, they're going to be available for bonding. Okay, so and these would be our valence electrons. So you count only the s and the p orbital to determine the valence electrons. How many electrons are in the s and the p? So in this case, we have 2 plus 3, which is going to be 5. So phosphorus has 5 valence electrons. Okay. So a lot of times what we'll do is we'll write it as N being any period. Then we'll put S and then X and then N, P, and then Y. So the N represents any period that we're talking about. And then of course you guys remember what the S stands for. The X would be the number of electrons that would be in that subshell. And then the same thing with the P. Okay, so these are some of the noble gas. I mean, some of the elements that are in the fourth period, and so you'll notice they have the number of, or their, sorry, I can't think straight. Their highest electron configuration. So this guy would be NS1. This guy would be NS2, NS2, NP1, NS2, NP2, NS3, and so on and so forth as we move across the periodic table, right? And so this is how you would draw the electron configuration. This guy has one valence electron, so we would make a dot, okay, around the sodium. So magnesium has two valence electrons, so it's going to end up being two dots, and so on and so forth, okay? So I'm actually going to let you guys go early today, if that's okay. And we'll pick this back up next week. Partially because my brain is about to explode, and I think yours is probably going to explode with me. We're almost done. We only have like 15 more slides, and they'll go pretty fast. But I think it'll be better to take it with a fresh head and give you a chance to practice a little bit. Actually, let's see if we can get through it. I think we can make it through it. It's not that much. We're almost to the goal. Okay, so it says write the electron configuration for the highest occupied level for group 6A 16. So we know that we don't really use the periodic table that has the 6A on it. So we're always going to use what is this group 16. Okay, and then if we go ahead and do that, so we're going to go ahead to group 16. Okay, and so now we need to find out how many electrons will we have in our s orbitals, in our s subshell, and how many are going to be in our p subshell if we're in this group. Okay, so how many electrons will we have in our s if we're going over to like oxygen? How many can the s orbital hold?
2.
2. Okay, so then we're going to have, it's going to write NS2. Okay, and then how many electrons would be in the P if we're talking about oxygen?
Would it be 6?
Just look at the in
1,
the P
2, 4.
4. That's right. Okay, so then that's what we would write for the highest, when we're talking about the highest occupied energy level. So then you'd always write it as NS2, NP6. NP4. Excuse me.
Wait, is this the valence electrons or no?
Yes, this is talking about those valence electrons. So in this case, oxygen has how many valence electrons? All you have to do is add the exponents.
Would it be 6 then?
6, that's right. Okay. So the second part says identify the group that has highest configuration of NS2 and P2. Let's do our periodic table again. Okay, so it says NS2, so we'll come over here, say 1, 2, and then NP2, 2. So we're talking about this group, right? Oh, I should have let you answer that. So we're talking about group 14, right? So that would be our answer. Okay. So we talked about Lewis structures. Now those dots represent valence electrons. So if we're talking about tellurium, we would count table, and we're talking again about electron configuration. So you only count the ones that are in the S and in the P, because those are going to be your highest numbers. This guy is going to be a 4, These are going to be 5s. So in the case of tellurium, we have a total of 1, 2, 3, 4, 5, 6 valence electrons. Okay. So then if we have 6 valence electrons, we're going to draw 6 dots around tellurium. So then we're going to do 1, 2, 4, 5, and 6. Okay, so that's how we would draw its Lewis structure. So it has to have 6 around it. It doesn't matter where they're at right now because electrons are always mobile, meaning that they can always move. And so we may be talking about what they are later on. Okay. Any questions? So counting the valence electrons, you're only counting the electrons that are going to be in the S and the P at the highest energy level. Now, there are trends that are going to be associated with the periodic table. As we move across the periodic table from left to right, the size of the atom is going to decrease. As we move from top to bottom, the size of the atom is going to increase. Okay, so let's put the periodic table up. Okay, so as we move in this direction, what's happening to the atom size? Is it getting bigger or is it getting smaller?
Smaller.
That's right, it's getting smaller. As we move in this direction, what's happening to the atom size?
It gets bigger. It increases.
That's right, it's getting bigger. Okay. Okay. So as we add energy levels, it's going to get bigger. So as we go down our energy levels, it's going to get bigger. And as we go within the same period across from left to right, it's going to be getting smaller. And that's because the number of protons in the center of the atoms, and since it's in the center of the atoms, protons are in the center of the atoms, they're going to do a better job of pulling in the electrons. And so that space is going to be smaller because you have more and more electrons as you move across the periodic table from left to right. Oh, the other thing is that you guys remember that the protons are in the nucleus, which are positively charged. And so again, those are going to cause your electrons to be pulled in. And so you're going to get a smaller space being occupied. So that's part of the reason why as we move from left to right, it gets smaller. And so this is an example of the size of the atoms on our periodic table. Oops. So this is just basically showing us the same thing. This is again a size, so it's going to increase as we move down, and it's going to increase as we move from left to right. I mean, from right to left. Refer to the atomic table and list atomic numbers 15, 16, and 33 in order of increasing atom size. Okay, so what is going to be the smallest atom? first thing that we want to do is find them on our periodic table. So we're talking about atomic numbers 16, 15, and 33. Okay, so can you guys find the atomic numbers on our periodic table? Are you guys there?
Okay, yeah.
Okay, so we're looking for 15.
That's phosphorus, right?
Phosphorus, that's right. 16,
Sulfur and
that's right,
then
and 33.
arsenic.
Okay, so what is going to be the order?
Right. We're putting them in order from what? From
Biggest
increasing.
to small, from smallest to biggest.
Oh, smallest to biggest. So wouldn't it be 15, 16, and oh no, 15, 33, 16?
Nope,
No.
you're right when you said 15.
Uh-huh.
Okay, but 15 is going to be bigger than sulfur. So 16 should come first. Sulfur should be the smallest. Then
Oh, it decreases that way, huh?
that's right.
Okay.
Then it's going to be 15
And then 33
and then 33 because 33 is going to be bigger because you're going to another level.
going down. Yeah.
Yep. Okay, so when we talk about the first ionization energy, so that's the energy that it's going to take to remove one electron from a from an atom. Okay. Now, when we talk about the second ionization energy, is the energy that it takes to remove one electron from an atom that's already removed one electron. If we talk about the third one, we're going to be adding one more electron to one that already has two that's already been removed. Okay, so that would be the third ionization. So if we look on a periodic table, as we move from left to right, so again, we're going in this direction. So we're moving from left to right. Our ionization energy is going to increase. So it's going to be harder to remove an electron. It's going to take more energy to remove an electron from as we move from left to right. Okay. And then as we move from top to bottom, it's going to take less energy. And so you're probably asking, well, excuse me, the metals themselves. So these guys like to lose electrons when they form ions. So they're okay with dropping maybe on one electron or two electrons, depending on where they're located. As we move across, these guys don't like to lose electrons. Their goal is to try to be like a noble gas. It's harder for them to be like a noble gas if they're losing electrons. They want to try to keep those electrons. And so because of that, as we move from left to right, the ionization energy is going to get harder. It's harder to pull something that wants to keep it, right? So if you have, let's say, if you have one kid and it is like your favorite kid or whatever like that, and somebody wants to try to take that kid away, you're probably going to fight them because you really want to keep that one kid, right? And that's your favorite kid. Now, so as we move from left to right, that ionization is going to increase because you want to keep those electrons. These guys want to keep their electrons over here, and these guys want to give them away. So they're going to have less ionization energy. It's going to be easier to pull off. As we move down further, in that case, they're so big that they probably won't even notice that they're losing electrons. And so they're not caring so much. But as you move from left to right, the ionization energy is going to increase again. And then it's going to be harder to get the electrons from elements that are on our right-hand side compared to the elements that are on our left-hand side. Okay. And we're in the home stretch. And so this here basically shows us. So this is a sodium atom. So if sodium loses one electron, it becomes positive. And it will also have the same electron as um, neon. Is it neon or helium? Let's take a look. Hold on. Right now, like I said, my brain isn't working. So we have sodium here. So then if we lose one electron, we'll have the same number of electrons as neon. Neon is noble. It's in a state that it's stable, right? And so since neon is stable, everybody wants to be like neon and all of the other noble gases. So sodium wants to be like neon. So if it loses one electron, it can be like neon. So it wants to lose an electron, where some other elements like fluorine is one away from being neon by adding one more electron. Since we add one more electron to this, it's going to act just like neon does. It's going to be stable. And so that's what it wants to be. So the probability of it losing an electron when it's only one away from being like a noble gas is going to be really, 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 really low because it's going to be trying to hold on to all of those electrons. Trying to hold on to those electrons, the ionization energy is going to be really high and it's going to be really hard to get rid of those electrons. The noble gases, those guys are already stable. They will not lose an electron unless you put a whole lot of energy in there. And so they're going to have a very, very high ionization energy so for them to be able to lose their electron. Okay. And so this here shows us, this here shows us that sodium here forming a sodium ion, so our Na plus, because we've lost one electron. And then this is just showing us the ionization energy. So here's hydrogen, here's helium, here's lithium, here's beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then neon. And you can see that the noble gases, it's harder to move electrons from the noble gases. And then it becomes really hard with fluorine as well too, because they're really strong. Okay, so we've talked about the second ionization energy. So that's just going to be the energy that's going to be required to remove an electron from an ion with a plus charge. And then a third ionization energy would be removing an electron from a atom that's already 2+. And so this is just a depiction of the trend for ionization energy. So list each of the following groups of elements in order of increasing first ionization energy.
So going from like biggest to smallest?
Yeah, so we're going from from the smallest to biggest.
Oh yes,
ionization energy.
yeah, left and right.
Okay. So let's first identify. So here's beryllium, here's nitrogen, and here's fluorine.
So then it's beryllium, nitrogen, and fluorine, right?
So it's in the order that they should be in.
Yeah.
Fluorine is going to have the highest ionization energy. The nitrogen is the second highest. Beryllium is
Yeah.
okay, so chemical families. So I like doing the periodic table for this. Okay. So we have group one metals, or we call them alkali metals. So, oops. Alkali metals, when they form ions, they're always going to be a +1 charge. In other words, when they lose that one electron, it's going to be a +1 charge. Group two metals, those are alkaline metals, alkaline earth metals. And so those guys, when they lose 2 electrons, they're going to be 2+ charge. Your group 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, those all contain the um, transition metals. And so those guys, they can change their charge. So they're not in any particular like way, like say we said group one will lose 1 electron when it forms an ion. And group two will lose 2 electrons when it forms an ion. Group three, it can change depending on what element we're talking. And then we also know that aluminum over here in group 13, that's always going to be a +3 charge when it forms an ion. Now, the thing about groups, group one metals or alkali metals, they're going to always behave similar to each other. And so they're going to have properties that are going to be similar to each other. So, like for instance, all of these metals, they react with water that's in the surface. They'll ignite when you're in the presence of water. So let me show you that. So here's lithium, here's sodium, and here's potassium. So lithium does the least, it foams just a little bit and gives a lot of heat. And then sodium, it sparks up. And then chromium, it definitely sparks up. I mean, not chromium, potassium. Right, it definitely sparks up. These two are very volatile, so they will react with water. Now, that's the same thing with chlorine, bromine, and iodine. So these guys are halogens. And the halogens, they're also known to be very reactive. They're so close to being a noble gas, they want to try to find that one electron that's out there. And so they're very volatile. So they'll ignite and stuff like that. Trying to get that one. Or the energy that's released after they get that one. Let's see. Okay, so this is just showing you how everything's laid out. If you go to P table, you can actually highlight the columns and everything like that. It's easy to remember. That's part of the reason I gave you guys the color periodic table. So we've talked about alkaline earth metals. We know that they're in group two. They have 2 valence electrons, and so when they form an ion, they're going to be a 2+. Halogens are group 17, and they always are going to have a valence electron of 7 valence electrons. And they're going to be so close to try to be a noble gas that they only need that 1 electron to sit there and get to stability. And so in that case, it's going to look, or they're going to look just like the noble gases when they get that 1 electron. So here is showing us the alkali metals. Here is showing us the alkali metals. You'll notice they're sitting there carving with a big old knife, but they make sure they have their gloves on. This one looks like it's already gone through the process already. It's starting to iodize a little bit. So we have the noble gases. So those are going to be unreactive elements. Sometimes they will react if you force them to with a lot of energy and time. So so these are the halogens, and so these are some how they look. And you guys have already heard of mustard gas. So that's just basically that chlorine. So then we have characteristics based upon the metallic properties. So a metal is going to be defined as a substance that is metallic and metallic properties of luster, ductility, malleability, and a good conductivity for heat and electricity. So they can lose an electron to form what we call a cation. A cation is a positive ion. And so when an electron loses its or when an atom loses its electron, it's going to become positive because it lost a negative charge. And so metallic characteristics are going to increase from right to left, and then across any of the rows, and then from top to bottom in a column. I hit it myself. Then we have nonmetals. Nonmetals are they don't possess any of the metallic properties. Ooh, sorry. And so those nonmetals are going to be dull, they're going to be brittle, and they're going to be poor conductors of heat and electricity. And then we have what we call nonmetals are going to form covalent bonds. And then they're also going to interact on, so nonmetals are going to form covalent bonds, and so they're going to form monoatomic anions in some cases, and then sometimes they're just going to form like molecules. And so those are all going to be important characteristics of the nonmetal, where the metal can also form what we call metallic bonds. And so there'll be alloys of metals, things to that extent. And then we have metalloids. Metalloids they have both properties of metals and nonmetals. Okay, so these are some things that we want to remember about metals. They tend to lose their electrons to form cations. They either have a valence of 1, 2, or 3. They have low ionization energy. They form compounds with nonmetals, but they can also do it with metals. They conduct electricity, high thermal conductivity, malleability, and ductility. So ductile basically means like it can be drawn out to wires, and then malleability means it can be hammered off to sheets. So nonmetals, they're gonna tend to form anions when they lose or when they gain electrons. So the more electrons you have, the closer you are to being a noble gas, you're going to try to get that electron, and you're going to have a negative charge associated with the product at the end of the year. So they have 4 or more valence electrons. They are high ionization energy. They form compounds with other metals and with non-metals. They are poor conductors of electricity, although carbon has been found to be an exception, or carbon graphite to be specific. They're going to be poor thermal conductivity, so they're going to be great at insulation, but poor at conducting heat or energy through that process. They're also brittle, and they also can be non-ductile. Okay, questions? Okay, so this is what it looks like. So your metals and your non-metals. And so this is how the metallic character is increasing. So we know that the metals, most of the metals are on the left-hand side. So if we're going from right to left, we're going to show that our metals, are they going to be more metallic as we move from right to left? Yeah, I think everybody tapped out. We're almost done. This is the last slide. Okay, so as we move from right to left, so we know that this is going to be the metallic characteristics are going to be more on the left-hand side than it is on the right-hand side. Okay, and that kind of makes sense because our non-metals are over here. So I'm going to put NM for non-metals, and then we have our metals over here. Okay, so and that's okay. So as we go from left to right, our metallic characteristic is going to get lower. As we go from Liberian in general, it's also going to get lower. Okay, metallic characteristics. Okay. Any questions? Okay. No questions? Okay, then I'm going to let you guys go because I'm about to pass out.